All right, thank you all for coming today. We're going to get started right on time here. Hopefully a few more people will drift in from other sessions. We're going to spend the first half hour or so talking about, in some depth, about the F1 FPGA instances, how they're used, what the use cases are, and walk you through the development process. And I move fairly quickly through that part of the presentation because I really want to get to motivating use cases. And we have Eric Stahlberg here from Frederick National Laboratory to talk about motivators for accelerated computing. So again, the agenda today, I want to talk briefly about F1, how it differs from other AWS instance types, how it's similar. I want to talk about the programming environment. And I'm going to make an assumption that you have little or no knowledge of FPGA programming, but I'll ask first, how many do have some FPGA programming experience? Well, that's actually a surprising number. Eric, you don't count. George, you don't count. Well, that's good. That's good. So we can go into a little bit of depth, and certainly in Q&A afterwards. I'll also direct you to some of the resources that are available on GitHub, on the community forum, and so forth. We'll also talk briefly about how applications are delivered, how you create an Amazon FPGA image, an AFI, and then either to deploy in your own applications or offer to third parties through a marketplace, how that works. And then, as I said, I'd like to back up a bit and talk about the real motivators for accelerated computing. And that would apply to GPUs and FPGAs, but specifically FPGAs. You know, what is driving us to do this, you know, on the cloud? So first, the goals of the F1 FPGA instances. We really did want to make FPGA acceleration capabilities accessible to dramatically more end users. There's absolutely applications that have been well proven for FPGA acceleration for many, many years. Areas like genomics processing, high-performance data analytics, image processing, video. These are applications that have existed for quite some time and have existed in the form of hardware-accelerated systems, appliances, if you will. That are used in a wide variety of industries and in the research sector. Another important motivator is just to make development of hardware-accelerated systems much, much easier and faster, in part by providing the development tools in the cloud in a very standardized environment, easy to access, easy to deploy. We also wanted, as part of that, to allow application developers working with FPGAs to really focus on the application itself, on the algorithms, not so much on the low-level issues of I/O and how do I communicate with RAM, how do I push data around. We really want to abstract that to the greatest extent possible while providing lots of options for different types of application architectures. And then finally, as I said before, providing that marketplace. So now somebody who's an expert perhaps in image processing, video processing, genomics, can offer their solution to other customers in the marketplace, as they do today with traditional software. To quickly review the AWS instance types, the EC2 instance types. As you know, we have a variety of these, and over time we've added more and more different types of EC2 instances. Some of these are quite specialized. For example, in the storage side, the i3 instance is quite specialized for extremely high IOPS, local attached storage types of applications, like scalable NoSQL databases, for example. The X1 instance is specialized for very high memory requirements, right? Large in-memory analytics, for example. And certainly on the right side, GPU acceleration has existed in the cloud for some time now, both for graphics acceleration. In the case of G2, that's its primary use case, and for compute acceleration, the P2 being a great example of that, recently released last year, based on NVIDIA K80 GPUs, specifically designed for compute acceleration with GPUs. Similarly, F1 offers the ability to do FPGA acceleration in a manner somewhat akin to what we do with the P2 GPU instances. So to basically summarize what an FPGA offers, and this applies to some extent to GPUs as well, it allows you to find those application hotspots, to find those opportunities to do things more efficiently and faster, to push those out to custom hardware, right? So you want to find maybe the inner code loops, maybe that kernel of computation that needs to be run extremely parallel, unroll the loops, pipeline things, push them out to hardware. This works very, very well if you can manage the data back and forth. If you're not bottlenecked, let's say, by tremendous amounts of I/O. Streaming, for example, video processing, genomics processing, streaming analytics, these are extremely good in FPGAs because they're heavily pipelined. So the F1 FPGA instance supports this by providing up to 8 high-density Xilinx UltraScale Plus FPGAs in a single instance. So each of these FPGAs is on a dedicated PCI Express card. You've got full access to them through the programming environments that I'll describe in a moment. And these are attached to a highly capable instance type. It's got quite a lot of memory, as you can see, a lot of vCPUs. It's based on Intel Broadwell processors. It's a very powerful instance type that's augmented by from either 1 or 8 FPGAs as PCI Express accelerators. Each of these accelerators, each of these FPGAs has access to local DDR4 memory, as you can see. So we've got the ability to move data down into the accelerator, put it in DDR4, access that memory, process, stream the data perhaps from one FPGA to another if you have an 8 FPGA application, and then move that data back to the host. That's the basic model of computation for F1. And we do have quite a lot of use cases that have driven FPGA acceleration in the cloud. This is not speculative. These are actual applications that are known to be acceleratable using programmable hardware. And a number of partners, a list here, there's more of course coming, who are developing applications or who have deployed applications on F1 instances. I see Rift in the room here today doing accelerated data analytics, Heterogeneous, for example, doing accelerated genomics. Many of these partners have previous experience or products that are FPGA-based as appliances, for example, and providing a cloud alternative in addition to their on-premise applications that are typically offered as appliances can be a great benefit to customers. We'll talk a bit later about the specific applications in life sciences, in cancer research. Eric Stahlberg will help us explain some of the motivators there. But it's important to know that across industries, across use cases, there are many, many opportunities to accelerate applications using FPGAs. I'm going to very quickly walk through the FPGA programming flow. There are 2 webinars available on the AWS YouTube channel that you can access more details on these. And as I'll describe, there's also resources, for example, on GitHub that you can go deeper into this. So I just want to summarize the 4 basic steps. The first step is to develop the hardware for your FPGA, the accelerator itself. And for that, you use FPGA programming tools that are supplied by the FPGA vendor, Xilinx, that are provided on AWS, really free, in terms of software licensing on AWS. You run those on a standard EC2 instance, and you have many choices, M4, for example, C4, R4, depending on the amount of memory and compute you need for your particular problem. You develop the application, you run synthesis, place and route, simulate it if you need to. Then when you're ready, you have your custom logic developed with those tools. You now are going to deploy that onto an F1 instance using what's called an AFI, an Amazon FPGA instance. Similar in concept to the AMI that's used, Amazon Machine Image, in an EC2 instance. And then if you wish, you can take your AMI plus the AFIs that are associated with it and offer those out on AWS Marketplace. Again, just to summarize, the AFI, Amazon FPGA image, similar to the AMI, is uniquely encrypted, identified. You can track it, you can secure it, offer it to customers, track its usage and so forth via the marketplace. It's also important to realize that you can have multiple AFIs associated with one application. So, very quickly, less than a second, you can swap out one AFI and swap in another one, right? To have a different hardware accelerated function for your application running in the AMI. So that first development step I described before, you use the developer AMI, the FPGA developer AMI that we provide. It's available actually on Marketplace. We don't charge for it. you will pay for the underlying EC2 instance that you're running the AMI, but you can choose from a variety of instances. For example, you might want to use the T2 instance, very low cost, to do the initial design and simulation, but then when it's time to do FPGA place and route, which is more memory and compute intensive, maybe at that point start to use an M4, R4, some other larger instance. So you have choices. So you use that developer AMI, whatever it takes you to develop your application, using higher level tools perhaps, OpenCL coming soon, or using VHDL and Verilog methods, traditional methods. Generate your application, your custom logic to deploy in the AFI using these tools. The developer AMI, as I said, that's available on Marketplace. We don't charge for it. It includes all of the FPGA tools that you need, specifically Xilinx Vivado on AWS with the necessary libraries. You combine that with a hardware development kit, an HDK that's available on GitHub to create your applications. That generates a file called a DCP, Design Checkpoint, that you can then combine with other aspects that we provide to create your complete AFI. I apologize, I'll go through that in more detail in a moment, speaking slower. The AWS HDK that I just mentioned and the SDK for the software side of the application are available on GitHub, and the address is there. So all of that code's available. The documentation continues to evolve and improve, but that makes it much easier to develop your application for F1. Now, you still need to have FPGA development experience, expertise, knowledge. These are somewhat specialized skills, but if you have experience with FPGAs in other platforms, you'll be able to start very quickly with the F1. If you don't have significant experience doing FPGA design, you can absolutely learn it as a software developer. One of the things that makes that learning easier is that we take care of a lot of the abstractions around hardware I/O. And that traditionally has been one of the more difficult aspects of developing for FPGAs. It's one thing to take an algorithm, an application, and embody that as a hardware, pipeline and parallel implementation using VHDL and Verilog. It's quite another thing to figure out how to talk to all of the I/O interfaces. And the FPGA shell that we provide as part of the HDK and the SDK on the software side to communicate to your application makes that much, much easier. And again, the HDK, the AXI interfaces, the interfaces to memory and so forth are all described in the documentation that's in that GitHub link for the HDK I mentioned a few moments ago. If you're familiar with Xilinx Vivado and related development tools, you'll use them in much the same way on AWS. You can either use them in an interactive mode, as we're showing here, for example, to run your HDL, your hardware simulations, or in this case, to run even JTAG type debugging with ChipScope, if you're familiar with that. Those are interactive tools. You can certainly run those in the cloud just as you do today. Remote desktop is basically what you're doing there. It's also possible, if you're interested, in running tools like the Xilinx ChipScope tools locally on your own machine and tunneling up to the FPGA to do things like emulated JTAG debugging from your desktop up into the cloud. That's described as well in the documentation. So at the end of this process, running the Vivado tools, generating that design checkpoint, submitting that design checkpoint into the tools that we provide for AFI management, you can now generate that AFI using tools that we provide. That AFI is secured, encrypted, given a unique ID. Now it's ready to be deployed on the FPGA that's attached to your F1 instance. And that deployment, well, this is the build step. So this is actually creating that AFI from the DCP. Again, all of these methods are described in the documentation. You can either do it with command line as we see here or through APIs. But at the end of that, you've got the AFI, you've created it, it's encrypted, and now you can download that to the FPGA to start an application. It's kind of a two-step process. First thing you want to do is get your application up and running on the F1 EC2 instance on the software side, and then through either a command line or API call, you can then download the AFI, select an AFI, and download it onto the FPGA. You can, as I said before, load different AFIs over time. So maybe your application needs to do, for image processing or video processing, maybe it needs to do some filtering application, and then maybe you want to swap that out and put in perhaps a machine learning inference application or something else completely different in that FPGA. And you can do that over time without rebooting the host EC2 instance. Now, what makes this possible from the software side is the SDK. The SDK includes APIs, command lines, and functions that allow you to do things like load and unload that AFI into the FPGA, or to write data, right, to get data from your host application down into the FPGA, into the local memory, and to actually interact with that FPGA from an application perspective. So there are management capabilities like managing the FPGA itself. There are runtimes that are used on the software side for that software communication with the FPGA. And then there's code that gets executed that we provide on the driver level to make it possible to communicate data to and from the FPGA. And again, this is all described in the documentation. I'm just summarizing it briefly here. When you're ready to download that AFI, here's an example of the command lines. There's two or three of them shown here. The first of these, FPGA describe local image, is basically saying what's in that FPGA at the moment. It's returning back that there's nothing loaded currently, so under FPGA image ID, nothing is loaded, it's empty. The next command line, FPGA load local image, is going to take a specific AFI that has a unique identifier and load that down onto the FPGA. And that should take less than a second to do. Now we do a describe image again. We will see that that image is successfully loaded in the FPGA. It's ready to execute. Again, this is just some of the SDK functions that are available to you, either a command line or API for your application. Communication with other customers, other users of F1 is available via the forums. We've got quite an active developer community. It's really starting before the public launch in the preview process. Quite a lot of customers and partners helping each other and communicating back to us. And our documentation, our APIs, our SDKs, HDKs have absolutely improved over time in response to customer feedback. It's a very active community. Feel free to join this and join in this discussion. We're going to talk briefly now about the marketplace, how that fits in, and then really turn it over to Eric to talk about, at a kind of a higher level, why we care about accelerated computing in large-scale applications, specifically in research. So the AWS marketplace has existed for quite some time as a way to allow third-party software providers to offer their solutions to other customers on AWS. And this includes literally thousands of applications provided by organizations that range from small startups with very specific applications, specific business needs, up to very large, well-known ISVs offering their solutions on the cloud, again, to other customers. And those other customers might be research customers, government customers, they might be large enterprises, but the ability to select applications from Marketplace, deploy those in your own virtual private cloud, your VPC, has been a very effective way for end customers and third-party ISVs to assemble solutions for their own customers quite quickly. The AFI builds upon this by allowing you to deliver the AMI, the Amazon Machine Image that encompasses your application, along with the AFI, or one or more AFIs, that actually provide that hardware acceleration for your application. This is very important for FPGA developers who historically have had challenges in delivering hardware-accelerated solutions to end customers, because not only did the end customer had to previously evaluate the software and the application and its ability to deliver on its promise of acceleration, they also had to qualify and bring in-house the hardware itself. which can be quite challenging from a compliance perspective or from simply an IT governance perspective. Bringing in custom hardware is not trivial for many organizations. And for the software provider, it's an expensive proposition to send out speculatively this custom hardware in order to have it evaluated. And doing this via marketplace on the cloud just makes it dramatically easier for developers of hardware-accelerated applications to take their solutions to other customers, take them to market, and actually monetize them in various methods, which could be, pay-per-hour types of methods, or long-term subscriptions, or other methods that are supported in Marketplace today. So if you're not familiar with AWS Marketplace and you're interested in developing FPGA-accelerated applications, please go have a look, and we can absolutely help you with that through the partner program. Just one example, and there's certainly more to come. The first application to appear on Marketplace was actually by Mipsology. Mipsology is providing a deep learning inference application, and this is really an example of what an organization can do in the FPGA. In this case, image classification algorithm implemented in the FPGA in F1, offered as a complete solution to other customers via Marketplace. And there'll be many more to come. So that was a really fast overview of the F1 instances, what the architectures are, what the development flow looks like. And again, there are absolutely many more details you can find in the GitHub repository I showed earlier. Also on the webinars that we published earlier this year, both an overview and a deeper dive some weeks ago. I'd like now to turn it over to Eric Stahlberg of Frederick National Laboratory to talk about the role of accelerated computing and why this is so important for computing today and in the future. Eric has a long history with FPGAs, knows them well, accelerators of all sorts, but I won't steal his thunder in providing too much information about Eric and his role. So thank you, Eric, for being here.
Thank you. We live? Thank you, David, for the opportunity to share with you several of the things that are underway at Frederick National Lab to accelerate cancer research. A lot of this is something that's becoming increasingly accessible to you all as the cancer research is taking full advantage of the opportunities that the cloud presents, both in sharing data and increasingly taking advantage of high-performance computing. To give you a quick overview, you'll see these slides, these points again. To give you a little bit of a context, as we mentioned, we're working to accelerate cancer research. Cancer is a devastating disease. It affects us all in many different ways. And so we want to accelerate the research in cancer in order to find solutions more quickly. We deal with rapidly growing volumes of data, requires advanced computing challenges to address, incorporate, take advantage of the information that's within that data. A few observations about how things are today is that increasingly the environments are heterogeneous. FPGAs are a component, GPUs are a component, CPUs are a component, and certainly there's architectures to come that we haven't yet thought of that we'll have to incorporate if we really want to accelerate cancer research. We have issues with moving data around. Presumably these are themes that you've all familiar with, may have experienced yourself, keeping the data stable. And increasingly, as we start building a knowledge network for cancer, how do we get the stability of the knowledge that's maintained within that data? And then as we look at a summary point, it's looking at the technologies continue to move rapidly. We need standards and representations that allow us to share our information and insight. And this is where you all come in. Innovations are key. So one of the things that has been part of my job for the past couple of years is to recognize that we can accelerate cancer research with the increasing levels of high-performance computing. We have a data glut. We have a personnel shortage. So all of you have an opportunity, potentially, to take your insights and take advantage of that expertise and apply it in a cancer research context. All right, this is how you get connected. One of the things that's been a priority of the Precision Medicine Initiative, that's what the PMI stands for, is about open science, supporting open access and getting open data, and even open source. So this theme of openness is what's making the cancer research accessible to you. standardization of various pieces, getting interoperability, getting a common vocabularies, ways that we can describe the data consistently, but then also services and infrastructure that make it possible. These, again, are themes that resonate with what we can do in the cloud. And what we can do in the cloud is take advantage of it to do these types of things. Come up with new treatments, ways to discover new drugs, take advantage of the data, and validate and find effective preclinical models that are increasingly personal, taking advantage of your own DNA, your own genetic context to understand how best to treat you. And that applies not only in cancer, but in precision health. And in doing that, we understand biology even more completely. And through that, we can actually identify the new drugs and new data coming through new techniques and transform cancer care ultimately by taking advantage of the advanced computation affecting the population and the load that cancer puts on all of us. So in the context of the Precision Medicine Initiative, working with the National Cancer Institute, they have 4 priority areas. In the upper right-hand side, you'll see one of the big issues is overcoming drug resistance. Cancer can be initially treated, but then overcoming that over time and maintaining that cancer in check becomes a challenge because cancer evolves. In the lower left, you'll see a reference to models, new ways to screen new drugs to affect the cancer both initially and as it evolves are priorities. And in the lower right, you'll see something that we're all familiar with, building a network of information. So part of what the NCI is doing in the context of precision oncology is building that network of information all the way from the molecular level to the patient level. Motivating what you see in the upper left-hand corner is developing new treatments that would be effective for the individuals who might be unfortunate enough to be affected by cancer. This all leads to generating lots of information. So if we look at the genomic information, you can see it's basically on a hockey stick curve. The computers are becoming more effective. We're using more automation in the generation of the information, essentially accelerating the flow of information. These are all good insights into the complexity of biology, which is extremely complex. It is one of the most difficult software problems you would ever imagine. The software is continuing to change. Your DNA is continuing to change. How it operates, and trying to understand that is going to take an awful lot of information. And so you see this rapid rise in information that you'll be available to take advantage of and understand that complexity. But today we see that traditionally HPC has been distinct from big data. Bringing them together has been a priority of the National Strategic Computing Initiative. And some of these observations are there, is that the data and the HPC have to come together. You know, the applications that we saw David refer to earlier are all applicable when we start looking at cancer. There's engineering challenges, big data challenges, curation challenges. All of those things apply. We have to deal with limits of how we can transmit and store data. We have to develop complicated analysis, share that insight, which ultimately gets us into collaborations, which require standards and other ways to work together. So getting back to the observations, as we start looking at exascale, very large systems, big data are key. Large problems, large analysis, complex, running things in ensembles and doing multiple trials to have the confidence in the solution of what's predicted. Research and development are also very important. This is where new algorithms and software come into play, where the FPGA having a resurgence. It's been a technology that's been around for years, which we'll see in just a moment. But using that in new ways to accelerate the research. Recognizing that we also have mobile health options and low power mobile technologies, clouds and analytics come into play. And ultimately, taking advantage of the marketplace and so forth of the entire scientific community to come up with new ways to solve these particular problems. So we start looking at FPGAs and recognize that it's not a small market. It's 7.2 billion by 2022, which means it's been established for a while. FPGAs are around, they just don't see them. What's happening now is they're becoming much more accessible and actually becoming much more needed as we try and achieve that high performance computing edge while maintaining the efficiency. And you'll see them in computer storage and medical applications, which is particularly applicable to cancer. But then again, all of these things begin to apply when we look at cancer. So on that road to efficiency and heterogeneity, we recognize that all the pieces have to work together. So the FPGA has a role, the GPU has a role, the CPU has a role, and we all have a role. One of the things that's happening right now is there's been a resurgence in artificial intelligence. AI has been around for a while, but we have the new context for deep learning, using graphics processors to train large-scale neural networks that will allow us to get value and information out of the data. That provides opportunities where we can actually then become more efficient, both in our storage and our computations, by using different accelerators and even different representations of the data. And so there's 3 key takeaway points. Heterogeneity is with us. It's going to continue to be with us as we start and press forward. Selective precision is important, because if we always use the same level of precision, we're not necessarily being as efficient or as effective as we can. And adaptability is going to be key, supporting those innovations that we have yet to see. So there's several challenges, and you can look up the source here. It's communications of the ACM. Data management issues, programming models, dealing with ensuring correctness of the result, which is important for scientific repeatability and reproducibility, and optimizing and even software engineering challenges. So these are all opportunities as well. One of the things that's clear is that every challenge is actually an opportunity waiting to be found and framed. Because if we didn't see it as a challenge, we wouldn't know that there was value in overcoming it. So those are both application-focused, and you can see several of those that are hardware-focused. Energy efficiency, high-performance interconnect, these are all possibilities that apply with an FPGA. So we see the opportunities for acceleration here. We recognize that we have large volumes of data. How do we work with that? How do we store it? And compression becomes one of those application spaces that an FPGA is particularly suited for. And again, I'm not biased towards FPGAs at all, because all the technologies that we have can accelerate it. Just using them in the right blend or in the right combination, and that's kind of the context for innovation. Data security is important. Preserving the privacy of the information, but also the integrity of the information is key to making the progress that we want to see in the cancer research. Increasingly, data reduction at the edge. You saw the spike in the amount of data that's generated. We're not going to necessarily be able to store everything, so at some point, we have to reduce down to what the essential information is that we would want to retain out of those instruments. Becomes increasingly important as we start looking at mobile health, the ability to monitor your biological response to different types of conditions and capturing that information. CERN, the collider over in Europe, they've been using FPGAs for a long time, dealing with the data reduction problem. So it's a proven case. It's just applied now in a medical and even in a health context. And ultimately, data processing and transformation is taking these large data sets and getting the value out of them, changing their representation, changing their forms. Image processing is a key one. In particular, you'll notice in the middle is that FPGAs are being used in artificial neural networks in the inference engines. We've already seen that as an example as well in David's presentation. So FPGAs are very valuable in that context. GPUs are effective in training, but we all have to put all this together, get data together. Ultimately, getting back down to what you see in the lower part is reproducibility and repeatability, because nothing accelerates faster than learning from others and not recreating the mistakes, not recreating and redoing the work. So ultimately, in the summary, just getting this, pulling together of how do we accelerate the cancer research, it's building partnerships, interdisciplinary, working together, looking at new technologies and getting new insights from scalable frameworks, cutting-edge predictive models, and even advances in machine learning. So there's efforts that are underway to take advantage of this. And revisiting some of these key points, accelerating the cancer research, the data volumes continue to grow. We have advanced computing technologies that we need to take advantage of to deal with that growing data that we're using to actually work and make progress on a very complex model, problem, challenge. The observations, heterogeneous computing, moving the computing to the data stability and knowledge are all key. We start looking at an FPGA. What's very nice about an FPGA is that once you create that image is stable. It's not necessarily going to be affected by libraries that would be loaded in, and so that it can improve the repeatability, the reproducibility. in that particular context, and recognize that technologies are continuing to advance. And we can't necessarily have chaos with everything advancing the same, so we need some elements of stability to manage and keep things going forward, not having to redo. And standards and representations and common sharing, important. So innovations are key. And that's where you all come back in, to actually take advantage of the opportunities that are presented as the data becomes much more open and available, to take the insights that you may have and see if there's ways that you can actually make contributions to what we're doing to actually accelerate the research on cancer. So thank you, David.
Thank you, Eric. How about for Eric?
Let's go for David.
Again, we're quite ahead of schedule. We blew through the early part of this quite quickly because we really do want to focus on the use cases. For those that are not experienced FPGA developers, I wanted to re-emphasize something that we covered earlier and that Eric covered as well. And that's the idea that heterogeneous computing is here. It's been here for quite some time. It's here to stay. It's relatively new to the cloud, but FPGAs have been around a long time. The use cases are well known. Those application developers who can get access to FPGAs, learn to use FPGAs, deploy FPGA-based solutions, they have a tremendous advantage in creating cost-effective, high-performance solutions, right? And one of the reasons to think about this in the cloud context, as Eric said, is that we need to bring the data together with the compute. And in areas like life sciences, genomics research, personalized medicine, and other areas as well, it's very, very important. Deep learning training, great example of this. It's very important that you have access to vast amounts of data. And so when deploying FPGA-based solutions on AWS, the fact that you have access to things like public data sets, right, ranging from satellite imagery to genomics data sets is very, very powerful. The fact that you have access to other types of compute and higher level services to use alongside your FPGA application is very, very powerful. So rather than the previous approach for FPGA computing, where it really was appliance-based, purpose-built hardware that had to be inserted into a data center and used in the context of other applications that may not play well with that appliance, it's going to be much, much easier to deploy these types of solutions in a cloud context. So I wanted to point you to a few resources online. If you're interested in more details around the F1 instances, the F1 landing page on the AWS website has a fair amount of information about the specifics of the instance type. I covered those briefly. The EC2 instance type, the Broadwell-based CPUs, the RAM and so forth. We didn't cover in detail the interconnect between the FPGAs, which is provided in a couple of different forms, a PCI Express fabric and a streaming interface. Those are covered in some detail on that landing page. If you're not familiar with the marketplace that I described before, dig into that a bit deeper, because that is the place where you will go to get, for example, your AMI for the dev AMI, for the developer AMI to develop the FPGA applications. That's also where you as a developer can offer your solutions to other customers, either free, right, or as something that you're monetizing, you're creating a business around. And the AMI and the AFI together encompass your complete application, and the marketplace is a great way to deliver that to end customers, track it, monetize it, and so forth. If you're in the research community, whether you're in the educational sector or research, we have a couple of programs of interest that have been covered certainly in other sessions as well. AWS Educate, which has programs, credits, for example, for individual students, for instructors, and for institutions, different types of programs, to make it easier for you to develop courseware around FPGA programming, around F1 instances, and AWS in general. And then AWS Research, which is more of a grants type of a program, right? So if you have an interesting project, you want to request some funding for that, put in a grant proposal, there's a process for that on the AWS Research page. And we're very, very interested in hearing from the FPGA community around applications that you'd like to try out, to deploy on the cloud. As I mentioned before, the public data sets are very important. So if you're doing maybe high-resolution image processing applications, you might be interested in the satellite imagery data sets that are out there. If you're doing genomics workloads, we have 1,000 genomes and other genomics data sets available on AWS today. You can access those. And there's many other data sets as well, Common Crawl, for example, to do analytics types of workloads. And a link here to Eric's team and what they're doing at Frederick National Labs, all kinds of interesting research. And research like that, highly compelling, right, from a research perspective, from a, from an application perspective, and just to see what hardware accelerated can do for us in a very, very important sector, right, of research. As I mentioned before, Eric has a long background on FPGAs. He's also been involved in the past in reconfigurable computing organizations, open FPGA and whatnot. So we really appreciate him coming today and offering some perspective on why FPGAs are so important in computing today and in the future, heterogeneous computing. So thank you again, Eric. Yeah, please. So the question is, does it play nice with Hadoop type of networking, which is more like a grid opportunity? So one of the benefits of running in the cloud, of course, for any instance type, including F1, is that you can scale out and deploy many, many F1 instances. Now, within the largest F1 16x large, I believe it's called, you have 8 FPGAs. Those are interconnected directly with PCI Express fabric and with streaming interface. To go from one F1 instance to another to create a cluster, a grid of them, that's going to go across the same high-performance networking that we have for other EC2 instances, for example, for the P2 instances. So those that are doing things like deep learning training on P2 GPU instances at scale, it's a similar concept to what you might do with the FPGAs. Yeah. Yes? So that's a great question. So will we be supporting partial reconfiguration of the FPGAs in the flow in the future? Well, actually, today with the FPGA shell and the custom logic that you insert into that shell, that is actually taking advantage of PR, of partial reconfiguration today in the Xilinx flow. Whether you can do that at a more granular level with the tools, we're interested in your feedback on the applications, how we might support that better. But partial reconfiguration is supported in the flow today, and we take advantage of that to combine the shell and the custom logic in the middle. Hope that answers your question. We can, yeah, thank you. Yes, please.
How well does the F1
Oh, OpenCL support. So OpenCL support is coming. We've announced that already, and that is part of the Xilinx tool set through SDXL that will be supported in F1 in the future. I don't have a time frame to share today, but if you come and talk to one of the product managers, perhaps we can shed a little more insight into that. Thank you. Other questions about FPGAs in general, specifically around F1? Yes, please. We're quite transparent about exactly what that chip is. That is a Xilinx UltraScale Plus VU9P. You can certainly acquire development boards and systems from Xilinx and other partners that use that device. So yes, the short answer is yes, you can use that same device yourself. Now, the development tools that we offer, the FPGA shell and so forth, those are all designed and optimized for use with the F1 instance in the cloud. So, there will be obviously some differences in using a physical FPGA board versus what you're doing in the cloud, but you can get access to that same device. It's commodity. I don't know this. So actually programming from the F1 instance, creating an application and running it, yeah, that's not something that we really have as a use case, but if you're interested in that, let us know what that use case might look like, and we're happy to listen and see if there's something we can do to support that. as Eric mentioned earlier, compute at the edge with FPGA-based devices in combination with compute in the cloud with FPGA-enabled applications is a very interesting use case. We're interested in hearing more about what you might want to do in that area. Yes?
A little late for this, but could you compare and contrast like GPUs versus like FPGAs?
Yeah, comparing and contrasting GPUs and FPGAs. I'll take a shot at that, and then Eric, maybe you can supply some experience as well.
Sure.
But you really have to think of GPUs as being built to take the same kernel of computation and parallelize it massively. For the original use case, of course, shaders that are used in graphics, right? So it is a SIMD machine, as they call it, single instruction, multiple data. It means you're just replicating that same thing. Now, over time, GPUs have become more complex, more control logic, and so forth. But fundamentally, that's what they are. A GPU has a fixed instruction set. It has a fixed data width. It's convenient to program. The instruction set means you can compile to it and so forth. If you look at an FPGA has no instruction set. It's flexible in terms of you can create any arbitrary pipeline of operations in it, and it doesn't have a fixed size of data. And Eric mentioned this as well. It doesn't have a fixed numeric precision. So if your application is optimized around 32 or 64 bits, as is traditional in the CPU world, that may actually not be the most optimal data width for the problem you're trying to solve. Certainly genomics,
Right.
you know, where you're doing basically 4 types, you could get away with far less bit precision in doing comparison of 2 genomic sequences, right, for example. Or if you're doing image processing, deep learning inference, you may only need very reduced precision. And so the ability to custom craft the instruction set and the precision you need and to create massively pipelined operations is really how FPGAs are different, fundamentally different from GPUs. But at the end of the day, they're both accelerating an application that otherwise would have been run in a more sequential manner. Eric, any other comments?
No, I would say the same thing in that particular context. You know, the GPUs obviously have their niche and the things that they can do well, and they continue to innovate and do more things well. But the FPGA itself, as David mentioned, is essentially a blank slate for innovation, creative new ways to come up with composites of what you might want to do, combining encryption, decryption, compression, and doing those things efficiently where it's not strictly a floating point operation. And having that essentially variable precision that allows you to take away and utilize not necessarily double, but potentially even quadruple if you needed to go to one extreme, or even down to bitwise, and still being able to do various types of analytics in that particular context. There's algorithms out there that will take advantage of essentially single-bit representations for graphs. You're just looking at edges and doing analysis in that way. And so if you were to actually be using a GPU, all the extra precision would essentially be unnecessary. Right? So there's opportunities to find that balance about what is going to be the most optimal solution for your particular problem, where the GPU provides essentially acceleration in a very stable configuration in a particular programming model. And the FPGA can be very complementary to that to give you the even further acceleration that you might not otherwise be able to achieve.
That's right. At the end of the day, you know, CPUs, GPUs, FPGAs, and whatever are to come in the future are very different. They serve different needs. There is some overlap, of course, but the types of applications that are best suited to a GPU could be quite different from the applications best suited for an FPGA.
Okay. They're really a complementary part of that ecosystem. There's various ways that you start looking at different programming models and how the FPGAs can be deployed. As we mentioned, it's not an immature industry. It's been around for years in telecommunications and so forth. And as the data and the big data problems become increasingly central to what we're trying to do, that transmission, that curation, that validation of the data, the movement of the data, which FPGAs have been doing for a long time, becomes increasingly central to the problem. And so we have yet to actually really achieve that real fusion that we bring the floating point capabilities of the GPU together with that data manipulation aspect of the FPGA. But that's where a lot of that innovation comes into play. And asking essentially all of you to go look, see what you can come up with, find those use cases that are important and compelling, and see what you can do.
Great. Thank you all so much. It's been an enjoyable session. Appreciate the great questions.